All right, now we are recording. So an m by n matrix U is called unitary. Yeah, it's a matrix with complex entries, basically. It's called unitary if U inverse is equal to U dagger. And sometimes people just write down this condition as U dagger U is equal to U dagger that's equal to identity. I think I'm going to say something more about this unitary matrices later. But in any case, so these are, let me write complex in here. So dagger is the transpose together with the complex conjugation. So U dagger is U transpose complex conjugation. You can think of it like that. And so as a result, this is the kind of complex analog of the orthogonal matrices. So in any case, so we are going to define UN as the unitary group. So let's say it like this, the set of n by n unitary matrices. I think I'm going to use this set constructor notation. So UN is the set of matrices. Let me use, yeah, U is on, right? So U is n by n unitary. Okay. In any case, you can show that the determinant of such a unitary matrix is of this form. It's a number with modulus 1. And if you just make sure that this number is equal to 1, so in that case, you get SUN. So that's the special unitary group. Special unitary group. Right? So that's basically the set of matrices U, where U is n by n unitary, and the determinant of U is equal to 1. All right. So you can easily see that since the determinant of U depends only on one real parameter, the dimension of SUN is just one less than the dimension of UN. Okay. So here I'm going to say that UN is a Lie group with dimension, I think that's n squared. SUN is a Lie group with dimension n squared minus 1. So in any case, these UN and SUN are important groups for particle physicists. So when you, I don't know, when you listen to a particle physicist, I'm sure that you have heard about this U3 and then whatever else, SU2 and things like that. I don't know if I'm going to talk about these kind of things, but if I ever talk about Lie groups, there's some kind of an association between the SU2 and SO3, sorry. SU2 and SO3 are somewhat similar to each other. They have the same dimension, both have both are three-dimensional, and if I have to talk about them, then I'm also going to talk about this association. There's some kind of a homomorphism between these two groups. I think, okay, so, all right. I think that's it, right, for matrices. But there's one matrix group that I would like to talk about. So just consider this matrix, let's say, A of X that's equal to, it's a 2 by 2 matrix of that form. I think I'm going to talk about this matrix later too. So in any case, it's not symmetric of anything. So there's always, it's actually called an upper triangular matrix. Upper triangular And these kind of matrices have this nice property that the product of two upper triangular matrices is also upper triangular. So there's some kind of an inclusion within that set. And then there are these diagonal entries are the eigenvalues and things like that. So in any case, you can easily see that by using this kind of an idea, the product of such matrices are of the same kind. But I'm going to do it explicitly. So I'm just going to take the product of AX with AY. So this is one. Let's talk about this product in here. You can easily see that this entry is, I don't know if you can easily see, but I'm just going to write it down like that. So this entry is X plus Y. And so as a result, this is AX plus Y. Okay. So if I take the X and Y as a real number, therefore, let's say it like this, the matrix group formed from these matrices AX for real numbers is isomorphic to the set of real numbers with addition as a group. Okay? Or we can think of this as one-dimensional translation group. Again, let's say that this is isomorphic to, right? This is the 1D translation group. If we remember 1D translation group, I just said that this can be defined as some kind of a transformation on the one-dimensional space. So a translation by X basically corresponds to shifting of all the coordinates by X. You can define it in some perhaps mathematical way, but I know that this group is isomorphic to the set of real numbers together with the addition. But I can think of that group also, or isomorphic to that matrix group, where the group operation is this time matrix multiplication. Okay? So this is basically, it's kind of interesting because I can describe an additive group as a multiplicative group. So let me say it like this. Any additive group can be described as a multiplicative group. Okay, let's see it like this. So as a result, there is no special significance for the group operation being an addition, right? I can equivalently describe this operation as a multiplication too, but with a suitable mathematical structure. So this is a nice trick, for example, because the translation group is actually a very, it's one of the symmetry groups that we work a lot in physics. So the translation symmetry is an important symmetry. So this is one way of actually describing this as a matrix group. So I can even go to the, I don't know, let's say it like this, A prime of, let's say, X, Y, Z, or X1, yeah, whatever, A prime of X, let's say. I'm going to define it like that. So this is 1, 1, 1, 1. I think these are X1, X2, X3. These entries are all equal to 0. So that's a 4x4 matrix. You can show that these matrices are also satisfy the same property, but this time the translation group is the three-dimensional translation group. And so as a result, I can easily say this. So therefore, the set of matrices formed by this, so that's X is equal to R3. This is isomorphic to the three-dimensional translation group. Okay. Yes. Yeah, I think that's going to be, that's correct, right? Um, uh, just check this, right? Check by yourself. So as a result, I mean, you can do these kind of tricks to actually describe things as a matrix group. Okay. So I'm done with matrix groups. So these are only the things that I'm going to say. I think I'm going to describe one permutation matrices at some point. But for now, I want to pass to some other kinds of, some other type of groups, basically permutations. And I'm going to spend some time on this. Okay, so I'm just going to consider a set. This is basically a discrete set. Yeah, let me say it like this. This is a set of n elements. N elements. N is just a number. This can be any set, actually. Sometimes, I mean, we might have, I mean, some kind of a geometric shape like that, which transforms, and we just consider the symmetries of that geometric shape, in which case we think about transformations that map this shape into itself. For such a case, we may actually number the corners like that, and then think of the set of corners as some kind of a set, and then consider the transformations between them. But in any case, we can do these kind of tricks. But to be able to define the permutation, let's just work with this, this number set, all right? But I mean, in general, these instead of numbers, we might have some other objects in there, some geometric objects as well, some other mathematical entities. Okay, so think about these functions. Let's say it like this: a function sorry. First of all, let me start what I'm defining. So a permutation on X is a function f that maps the elements of this X into X, which is 1 to 1 and onto. Right, let me describe it like this, but just keep in mind that if it is 1 to 1, then it's necessarily onto, because X is a finite set, right? Or if it is onto, then it is necessarily 1 to 1, because there's some kind of an association in there. So, so basically, F basically sends each element, for example, sends 1 to some other element in here, which is F of 1, sends 2 into F of 2, and so on. And so as a result, each element is mapped to a distinct element, F of 3. So as a result, there's this kind of an association, one-to-one association between maps. Let me also say this. I think I'm going to use a different color in here. This statement basically implies that F is invertible, meaning that the inverse of that map, that transformation exists. So there is an inverse. So as a result, then if you just consider the set of all of permutations on this set, this has to be a group then. So we just define Sn, which is defined as the set of all permutations on X, just keep in mind that this is just an n element set, right? So we just call the set of all permutations on X. So we can then show that Sn is a group. Its name is called the symmetric group. I don't know why people call this like that. It's called a symmetric group. But this is one of the important groups that in physics, because, I mean, there's this natural symmetry in quantum mechanics, the particle exchange symmetry. So as a result, if there are n particles, n identical particles, we would describe the symmetry of these particles by that permutation group, right? And for that reason, this is important. But I don't think that we are going to discuss this kind of a symmetry in that course. But I mean, this is one of the reasons why we are interested in this group. Okay. Why is this a group? So first of all, consider the identity permutation. I'm going to call this as E. E basically has the property that E of I is equal to I for all I. All right? It's basically a permutation that maps itself. So there is this group operation is the function composition. Group operation is the function composition. Okay, so basically if F and G are two permutations, then there's this thing called F of G. This is basically the function composition, all right? So that essentially means that the F of G applied on, as a function applied on I, is the same thing as F applied on G applied on I, all right? I mean, we are going to define it like this. So as a result, keep this definition in mind. So we are defining every permutation as a function, and the group operation is basically the function composition. So you know this property beforehand. Okay, so we will argue at some point that Sn, when n is bigger than 3, is non-abelian. So therefore, whether composition is f of g or g of f, it matters. So as a result, f of g is usually different from g of f. So therefore, the order is important. And to be able to compute the product of two permutations, for example, you have to remember that rule, all right? We're basically doing this function composition in here. Okay. So, all right. So I know that, I don't know, there's an inverse for each permutation. And then I know that the composition of this thing with together with the function itself gives us the identity and things like that, all right? So let's just forget about these kind of details. So you can easily see that this is really a group. This, I mean, the set of permutations is really a group. Then I'll be talking about some mathematical representations of permutations. Right. I'm going to offer two expressions, actually. Mathematical should I call representation? I don't want to call it representation because we are using representation for with a precise meaning. So mathematical ways to express a permutation. Okay, so this is the first one. This is the tabular way. This is a notation that you are going to note, you're going to find in a lot of places. So what you do is like you just write down the numbers, the set in here as a row, And then below the row, you just write down um, the numbers which are mapped by this function. Okay. So that's f of n. So that means, for example, identity, I don't know, let's say it like this. In S4, for example, identity would be represented by this table, right? We're not thinking of these as matrices. It's not a matrix. It's just a table that tells you how to evaluate certain things. And for example, I don't know, there might be some element permutation, for example, where 1 is mapped into 2, 2 is mapped into 4, 3 is mapped into 3, and 4 is mapped into 1, for example. Okay. So that's a non-trivial permutation, in which case I'm going to understand that, for example, f of 1 is equal to 2. And let me give one example in here. I think I'm going to write G as, for example, let's say that this is 1, 1, 2, 4, 2, 3, 2, 4, 4. So to compute G of f, therefore, I need to consider how this is transformed, how this sequence is basically set of numbers is transformed. So f, first of all, transforms this to that set of numbers, because I'm just writing this row in here. Sorry, to that row in here, all right? And then what I do is I now apply G to that set of numbers. I know that G, for example, maps 1 into 1 and 4 into 4. And so 2 is mapped into 3 and 3 is mapped into 2. So this part is slightly non-trivial. So therefore, G of f would be 1, 2, 3, 4, and 3, 4, 2, 1. Okay. So as a result, G of f would be that permutation. Let me say, etc. in here. I don't want to go into more examples, but you can check if G of f is the same thing as f of g, for example. Okay, so that's the one thing in here. So I would like to go over this example. All right, I'm just going to do something else in here. So I think, yeah, let me continue from somewhere below, all right? So I'm going to take this example again. Why the same example? I don't know. 2, 4, 2, 4, 3, 1. All right, so let me talk about this first of all. So, right, there is a sequence of elements of this set X in here. But this is just a sequence, right? Sequence of elements of X ordered in some particular way. And in physics, for example, in some certain applications in physics, I mean, we actually deal with these kind of sequences in some certain situations. And so as a result, some people also call these sequences as a permutation as well, right? Some call these sequences as permutations as well. But keep in mind that, well, basically there's some kind of an association between the permutations as functions and such kind of sequences as, yeah, whatever. So there's a one-to-one correspondence, basically. This is nice to know, But do not confuse between these two, right? So I know that you have learned about permutations in high school as these kind of sequences. You have counted these permutations. So you know that for example, if you do this counting, I mean, you can easily see that the number of such sequences is equal to n factorial. So there is this is one statement in here that we can immediately write in here. So the number of permutations of an n element set is equal to n factorial. So therefore, this is the same as the group of order of the symmetric group Sn. Okay, so this is a different way of looking at the permutations. So this particular way of looking at it is useful sometimes, but please do not forget that we always define a permutation as a function. So as a result, if you would like to think of these sequences as permutations, you just think of them as the function applied to that standard sequence, and you get this other sequence. So always think of the permutations as functions, right? That's going to be an important point of view. At some point, we are going to define even and odd permutations. So as a result, I'm going to describe the evenness and the oddness of the permutation by just looking at that sequence. But we still have time for this, right? So let's talk about something else. So I'm still talking about the same f again. 2, 4, 3, 1. So sometimes we would like to describe this transformation as some kind of in a pictorial way, basically. So you can see that f basically maps 1 into 2 and 2 into 4 and 4 into 1. Yeah, once we come back to 1, then we know how 1 is transformed into 2 and so on. And then 3 is transformed into 3. Okay. So these are called basically the cycles of that permutation. So let me say it like this. A cycle of a permutation G, permutation's name is G, is a sequence of elements of X. Let me call them like, I don't know, I1, I2, let's say IM, such that basically G maps I1 into the next element in the sequence and maps I2 into I3 and so on, and maps the last one into the first element. Okay, I mean, the pictorial way is perhaps the best way. So I1, I2, and so on, dot, 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 and then we have IM in here. So G is a map that maps I1 into I2, I2 into I3, and so on. And at the end, of course, somehow this should come back. And as a result, the last entry should be mapped into the first entry. So as a result, there is a cycle formed in there. Okay. So as a result, for example, this permutation in here, right? F has a cycle that I'm going to denote by 1, 2, 4, right? Because 1 is mapped into 2, 2 is into 4, and 4 into 1. I can also say the same, express the same cycle as 2, 4, 1. That's basically the same cycle. Because in a cycle, there is no definite starting point. So you can start anywhere. So I can also start from from 4, and then 4, 1, 2 is also the the name of the cycle. Okay, so these kind of cycles is basically called a tree cycle. So this is an M cycle because there are M entries in there. So this is a tree cycle, right? F also has a 1 cycle, which is 3. Okay, so what was it? Yeah, it was in here. So the 3 is mapped into itself. So therefore, this is a 1 cycle. Okay, so there is something called a cycle notation. So that's the second type of notation. Cycle notation for permutations. So basically, we express this, the permutation, by just listing each of the cycles. So as a result, F would be basically described like that. So that's an element of S4. So you just write down the cycles in here. So in this way, you express the permutation in an economical way, basically, by just writing less number of symbols on the paper. You can express the permutation. So as a result, we prefer this cycle notation over the other ones. There's an identity, for example. Identity in that case has only the 1 cycles because each element is mapped into itself. So let's say it like this. Identity has only 1 cycles. And so in any case, so as a result, by showing these cycles somehow, we can uniquely identify what the permutation is. So I'm just going to give you one more example, perhaps. So I don't know, let's say, for example, H in S to 8. Why 8? I don't know. So H is equal to 1, 7, 4, 2, 3, 5, 6, 8, right? So 5, 6, 8, 5, 6, and 8. I don't know. It's a very complicated thing, but in any case, so we know what, I mean, there are these cycles in here. So there's this 4 cycle. I'm just going to quickly show it like this. So it basically maps 1 into 7, 7 into 4, 4 into 2, and 2 back into 1. I have 5 is transformed into 6, and 6 into 5. And then 3 is mapped into itself. 8 is mapped into itself. Okay, so as a result, we have a 4 cycle, 2 cycle, and 1 cycle. This is not unique. This expression is not unique because I can express any cycle starting with any element, right? So instead of writing this as like 1742, I can express it as 7421. The order is also unimportant, so I can write this 5, 6 as like this way, and then we have 8 and 3, right? I can change the orders, so that's 5, 6, and 2, 1, 7, 4, and then 3, and perhaps I can add the 8 in here, etc. So it's not unique, but there's a kind of a practical way of expressing it. Okay, there's one more thing. So that's a notation. Notational simplification. Right? we don't usually show the one cycles in the notation. So there are some one cycles in here, but we just drop them. So whenever you see a number dropped, you then understand that that number should be a one cycle. So as a result, this is a common notation people choose to use, and this actually considerably simplifies the expression in here. So we don't usually show the one cycles in the notation. So let me say the identity. Identity has this notation, obviously, right? If you think about it. So it just goes on like that. In any case, identity is shown by E only. So we use the E notation for the identity. Okay, so that's a convention that I'm going to follow. So as a result, let me use yellow colors in here. So for example, this particular permutation, I'm just going to write 562174. I'm not going to show 3 and 8. And once you notice that the 3 is missing in that expression, you would understand that this has to be a one cycle, right? In the previous example, for example, I'm going to show this as 1, 2, 4. Okay. I'm not done. So I'm going to use the cycle notation all the time. So let's just remember this. Therefore, S1 is basically the group that has only the identity. So that's the trivial one. Trivial. Yeah, let me just say it like this. This is cyclic group of order 1. This is uninteresting. The permutation group of 2 elements is just this one. The symmetric group is basically has these 2 elements in here. We meet this group in applications a lot. But in any case, there are only 2 permutations. Either they remain the same or you just switch their places. So that's also is isomorphic to the cyclic group. So these are very simple groups. The first non-trivial symmetric group is of order 3. There are 6 elements in there. So I'm just going to show them like this. So there is this identity. There are these 2 cycles, 1, 2, 3, and 1, 3, 2. And then there are 3 2 cycles. So that's 1, 2, 1, 3, 2, 3. So as you can see, S3 has 6 elements. Now I can show that S3 is non-abelian, but I will show this only for abelian by just giving an example. So the proof is like that. So I'm going to just do some calculation in here, and it's just the product of 1, 2 multiplied with 1, 2, 3, and I'm going to do the same kind of a multiplication in the opposite order. So I'm going to show that, the product of this element with that element depends on the order that you multiply them. And so as a result, this shows that the group is non-abelian. But let's see what this implies. I'll try to show it how we can compute this kind of a thing. I do it actually from my without writing anything down, all right? So what I do is this. So I'm going to start a cycle, right? So I know that this whole expression is a permutation. So if it's a permutation, it sends the element 1 into something, either itself to some other element, and I would like to find what that element is. Okay, So as a result, I try to understand which element this one is sent. So I basically first think of that. I'm applying this permutation to one, and whatever I get, I'm going to apply the second permutation to that element. Okay, but I'm going to do it mentally. So first, one is sent into two by the first permutation. And then I apply the second permutation, then two is mapped into one. So as a result, one is sent to itself. All right? Once I complete that cycle, I start with the second cycle. So let's consider what which element two is mapped into. So the first permutation is applied on two. What do I get? The first permutation sends the 2 into 3, all right? So as a result, I get 3, sorry about this, 2 into 3, yes. And then I apply the second permutation. But in the second permutation, 3 is just fixed at itself. So as a result, the 2 is mapped into 3. And I continue with this. So now what happens if these two permutations are applied on 3? It is obvious in here, but let's just continue in any case. So the first permutation sends 3 into 1. So I get 1 now. And the second permutation sends 1 into 2. And so therefore 3 is mapped into 2. Okay. So as a result, 3 is mapped into 2, but we just completed the cycle in here. So as a result, I write down the cycle like that. So the result is 2, 3. I can do the calculation like that. So 1, 2, 3 permutation is, in the table notation, corresponds to this. 1 is mapped into 2, 2 is mapped into 3, and 3 is mapped into 1. And 1, 2 permutation corresponds to this. 1 is mapped into 2, 2 is mapped into 1, and 3 is mapped into 3. And what I do is like I just multiply these two. Okay, so we just do this thing in here that we have done above. So this is what the first permutation does, maps 1 into 2, and so on. What does the second permutation do? It sends 1 into 2 and 2 into 1. So that's, this 2 is mapped into 1, 1 is mapped into 2, and 3 is mapped into 3. So therefore, this is the permutation 1, 2, 3, 1, 3, 2. Which basically says that, well, it just fixes 1 and maps 2 and 3 into each other. And so as a result, this is the final result. Okay, so let me state it like this. I mean, you can do the same calculation with the tabular notation. If you're not comfortable with the cyclic notation, you can do this. But I suggest that you actually think about the cycle notation. You have to be a little bit careful with this, but in any case, you can easily do it. So I'm going to do this calculation now. So first I apply this permutation and then that permutation. So start with 1. 1 is mapped into 2 by the first thing. And 2 is mapped into 3 by the second one. So that means 1 is mapped into 3. Now what happens if I apply these permutations to number 3? First permutation leaves 3 as it is, so we have 3. Second permutation maps 3 into 1, so the final result is 1, which means 3 is mapped into 1, so therefore we get this. I don't want to repeat the same argument for 2. You will notice that 2 is mapped into 1 by this, so therefore this permutation is 1, 3. So that means this product is not the same thing as the product in the opposite order, which means S3 is non-abelian. Okay, this is the smallest non-abelian group. I have talked about this before. We don't have any other non-abelian groups with smaller order. This is the smallest one. That is why we are going to use this group as an example for most of our calculations, right? So that's a very nice example, actually. So, all right, let me leave it in here. Next, on Wednesday, I'm going to talk about this evenness and the oddness of permutations. That's an important concept. We will talk about it. And then we will talk about the subgroups of the permutation groups, the subgroups of Sn, the permutation groups. And then what else? Yeah, I'm going to talk about permutation matrices. So let me just write them down in here. So next, so that I don't forget. Even and odd permutations. I'll talk about permutation groups. Basically, these are subgroups of the full permutation group. And then I'm going to talk about permutation matrices. So just like any other groups, I can basically represent the permutations as matrix multiplication, and the permutation matrices become very useful for that. So we are going to use all of these machinery later on, and that's why I'm spending some time on this. And so as a result, we will continue with this on Wednesday. Right, let me first stop the recording.